And now this problem in our current example here is a problem that came out from the work of many economic experts right here, or for people who are studying business, especially the financial analysts. Okay, and so here let's spend some time reading the description, the wording description of the problem. So when an initial amount of money, so the amount here is called A, the initial amount in dollars, is invested into an account that earns interest continuously. The future value of the account after T years is given by the formula. So future value, that makes sense why they named the function, our function modeling the amount of the future amount here being F, capital F. So F of T equals A, the initial amount of money, times e to the RT. And the explanation here is that R is the annual interest rate earned by the account. Okay. So now let me pause it a little bit. Of course, I am not a financial expert myself, but there are a couple concepts I can explain right here. But then for the rest, for any other complicated understanding, then let's leave that for the financial experts to clarify and to explain. Okay, but so the first term that we ran in here is, you see, it doesn't have, it doesn't have to be just financial experts to deal with these problems. It's actually, it can happen for, and the reason I brought it is this in my video lecture here, because any one of us is investing our money. So we're investing to build a future amount for maybe for us to enjoy ourselves, or for our kids to go to college, or for us to save up for a house or something like that. So the idea now is that as we put some starting amount of money, A, okay, so A is initial amount, just like that, because the day we step into the bank and open up a saving account or any account that earns interest, right, then we're bringing in some initial amount. That's what it called right there. So initial amount. And the good thing with this kind of investment is that it's the way how our banking system works. But the good thing is that once we give the money to the banks, right, for investment, then depending on the different bank they offer, but the money grows itself because there's the interest. The idea of interest, and like I said, I don't want to step too far into any of the financial understanding or economic understanding, but the idea is that when we are investing our money, right, technically the bank is borrowing our money to do better their business whatsoever. So the interest idea, the concept of the interest is that they are paying us. And so that's why we got the interest. It just means we earn more money based on what we lend out. Okay, so we lend out this initial amount to the bank. And the interest is the bank paying us, what the bank paying us. But so now, for the concept of interest right here, they are periodic interest, which is more common to a lot of people. Periodic interest. It means we get interest. We get interest paid. It could be every monthly, which is the most common. It could be monthly. It could be yearly, meaning we earn interest every month if it's a monthly plan. We earn interest every year if it's a yearly plan, or we can earn interest on a daily basis right there. Or we can earn interest in every quarterly, meaning every 3 months. Okay, there are so many different basics, different plans out there that the bank can offer for you. Okay, but so far among the common plans, like the daily is the one that's kind of like in the shorter time amount, because so basically you earn interest every day. But there are also the kind of plan that's your money continuously produce interest. And that's why, in your problem here earlier in the wording of the problem, in case you might wonder, see, it earns interest continuously. So it's even, you continuously earn every instance after, the idea is, once I highlighted that term, the idea is every instance after you give the money to the bank, then your money start producing interest. And it don't even worry about is that every second. That's not the point anymore. It's every instance of time after you invest your money into the bank. It's going to keep producing money. And so it's even more regularly, even more continuously than being daily. Okay? And that's the idea right there. But exactly how it works and how they derive the equation, I'm going to leave that for the financial and economic experts to explain in all that, because that's their expertise. Okay, but now, generally this is what we learn. So according to the description of the problem, we know that our money is earning interest continuously. And so anytime, according to the rule for that the economic experts have found, then anytime the money, you're going with a continuous earning interest plan right there, then your modeling function is an exponential function where it's a times e to the RT right here. Okay, so now again I'm going to spend some time rewriting that function. So future value, that means 10 days later, 10 years later, 20 years later, however long you want to be. Okay, how long your investment is, that's actually something you have to decide with the bank right there. But so now F stands for future value. It depends on how much you started out. It makes sense that way, right? I mean, you only walk into the bank with $5, then maybe 30 years, 40 years later, you will earn something, but it's not as much as the person who initially came in with 5,000. Okay, but your future value, it was proven that will always be dependent somehow on the initial amount, and so that initial amount being multiplied with the exponential function e to the RT. So it makes sense now that t is time, because time is what decides how much money you will earn. Okay, 20 years later, 30 years later. But this R right here, as being explained in the wording of the problem, then R is being understood as the annual interest rate. Okay, so, and that's why, see the R here, R is the annual interest rate, but how is that connect with being continuous? Because continuous here means we keep producing every instance of it doesn't have to be that long, being a year. So how that connects, I have to leave that for the economic experts to explain right there. But so as the formula here says, then we can directly work with that. So R here is just basically the interest rates. Okay, and that's for shorts, the interest rate. Okay, and on standard it's annually. So now in our problem, according to the given information, then in our problem we have initial amount. We walk in the bank on that day with $8,000. So that is our initial amount right there. And then the interest rate here is 5.3% annually. This is, think about, that's what the bank offer for us. Okay, and so at different time in the history, banks offer different interest rates for investment. Okay, and that's what it could be very beneficial for anyone who are interested in going for investment. Then you're gonna have to constantly watch for the interest rates before you actually decide when it's a good time to do to do investment. Okay, and so now, but after all that, and I promise this is the end. I don't want to step too far into the job, the expertise of the economic expert. But so our problem here, we are given A equals 8,000. Okay, and the interest rate, the wording, and I hate to keep hitting back into the way how experts work. But a lot of time when we communicate with financial experts, we use percentages. It's a common way among the economic experts and all that. We communicate interest rate in terms of percentages. But be careful, when we actually put that into a mathematical formula, then it will become, so here's how it looks. So our formulated future value is 8,000, makes sense that way, initial amount, multiplied with E, but this interest rate here has to be written as a 0.053 right there. Okay, so keep an eye on that. When we communicate with anybody else who is doing investment and things like that, we always say, hey, my interest rate is 5.3%, my interest rate is 1.5%, things like that. We're using percentages as a term we speak. But when we're actually using that in a mathematical model like this, we got to use the real decimal. So the reason I came to 0.053 right here, because simply 5.3 divided by 100, we get 0.053. So this is 8,000 e to the 0.053 t. That's our formulated and our concluded modeling function for whoever doing the investments under this plan. And the plan I'm talking about, he walked in a bank, or he or she walked in a bank with $8,000, and the bank offered interest rate 5.3 annually, but at continuous interest. Okay, this is continuous. Okay, continuous earning for the interest. All right, and so now, once we have a clear, solid understanding of the problem, now we are looking back one more shot into the wording of the problem. So now in the actual question, it's asking for what is the value of the account. What is the value? I mean, it should have been what is the value in the account to be accurate. Okay, so what is the value in the account in dollars after 25 years? Okay, after 25 years. So what it means now is that once we have found our function to model the future value, of course, right at the instant you are here in the bank and giving in your money for investment, you only have 8,000. But the question now is that how much are you going to have totally, right? Including the one you already put in. How much are you going to have in 25 years? Of course, I mean, ideally, once you leave it there, you lock it up for that long time amount, of long time. You lock it up without any withdrawal. Okay, let's talk about the kind of long-term saving plan, so that when you finish with your term right there, then that's when you're gonna take your money out. Okay, then in that way, question in part A is simply looking for F at 25. Simply just that. We're substituting 25 years into our modeling function for future value. And so now we're looking at 8,000 times the E, okay, to the, see, now I have explained already. The interest rate here expressed here have to be, the interest rate to be expressed here has to be 0.053. And we're multiplying that in the exponential part, 25. All right, so that's how we are substituting value in. And now let's start doing the calculation. I'm going to need a couple of minutes here to get my calculator ready for that. All right, so my final calculation came out being 30097.48. Okay, and it for financial math, without the need for me to tell anyone, we go with 2 decimal places. So make sure you round properly for that. But why is that? Because it's our currency system. We go with cents and all that. So 2 decimals. That's what our money is. All right. And so look at how much we can earn in 25 years. We walked in the day we walked into the bank, on that day we started to do the investment. We only came in the bank with 8,000. But 25 years later, we've got that much. I mean, the 8,000 initially we brought in is also part of that. See what I'm saying now? But then this is a problem it brings up for any of you to be aware about how your future value can produce for you. But of course, ideally, this is too nice for an actual interest rate. I mean, usually in real practical situation, the interest rates are a lot lower than this. Because otherwise, if everybody is earning that quickly, then the banks is not doing a good business for them. Okay, so just be aware of that. But that's how these functions run. So now let's get into part B of the example. All right, so now in the question of part B, we're looking for, so the question is asking what is the exact instantaneous rate of change, okay, of the value in the account at exactly 17 years. Exactly 17 years, okay? And this problem was even a little nice to be clear that we're looking for the instantaneous rate of change, even though we already agreed after our general description that any kind of rate of change we're learning in these days, okay, is an instantaneous rate of change. And so now, being clear with what we're looking for, then once again, I'm going to keep my modeling function right here. It's 8,000 e to the 0.053 t, okay? But now, the actual problem itself is looking for the actual problem is looking for the instantaneous. So relative to the beginning function, then the instantaneous rate of change is the derivative of our future value function. Okay, and so now that means I'm looking for f prime, but f prime at exactly the wording set, exactly 17 years after the day we start the investment. So f prime at 17. Okay, and so that's the idea of the problem. So one more time, let's have a look at our modeling function before I'm completely staying on this other board. So our function here, our future value function is it's 8,000 e to the 0.053 t right here. So now we are going to find the general derivative. So this is our goal, but now to get that goal, we need to find the general f prime at t. Okay, and so the general f prime of t here says, well, it's going to be 8,000 as the constant coefficient stays there times e to the 0.053 t. Okay, but now that part here was the inside of our exponential function. So chain rule says we need to multiply with the derivative of that inside, which gives me 0.053. All right, so now we have found the derivative of our function. Okay, and so let me spend a little time right here to calculate, to multiply these two quick little numbers together. So point. All right, so our final expression for the general derivative of f of the future value function is going to be 424. So f prime at t is 424 times e to the positive 0.053 t. Okay, and so now once we have had our instantaneous rate of change as the derivative of our general future value function, then now our goal is ready for getting it, for catching it. F prime at 17 is going to be 424 multiplied with e to the 0.053 t. Wait, I forgot to substitute in, but we need to substitute that 17 in there. Okay, and so now at this point we are ready for a final calculation. So my calculation here says, according to my calculation, I'm looking at 1043 point, and without me telling you, everybody should know that we go with 2 decimals. So 0.91 here, and that's dollars. So what is the meaning of this value? That's our values right there, but we're earning, okay, dollars, okay, per year. But that rate is only an instantaneous rate. Okay, so the next instant it's going to change. Okay, and so now I am going to look into the next question. So at what time in years is the instantaneous rate of change of the value in the account increasing by 938.92 per year? Okay, so increasing. Now this is the term that I could have also mentioned right after we've had at the end of our example of part A. So let me quickly swing back to that, and then we're gonna get back to this problem right here. But you see the answer we've had here was a positive answer. So it's a positive rate of change. That means in the end our money is still growing, it's still increasing, and that's why, you know, having a positive rate of change, that means we're increasing. Okay, and that's the reason why in this problem, when it's asking when we're about heading out for part C right here, okay, so what is the rate when our money is increasing, the value in the account is increasing by at the rate 938.92 per year. So now, in other words, here's the setup for the problem right here. I'm going to spend some time, or maybe let me use the other board right there. Our general derivative, our general rate of change, instantaneous rate of change for future value is 424 e to the 0.053t. Okay, that's the general instantaneous rate of change. But we want that to happen at 938.92 dollars per year. Okay, so now once we've done that, then we set up for ourselves a goal. We want to solve for t. Why do we solve for t? First of all, t is the variable for time, and the question was asking for at what time in years, or in other words, how many years after the day we invest, so that the rate was happening at was increasing at 938.92 per year. Okay, and so that's the reason why we are solving for the variable t right here. Okay, so now what the derivative is what we already had, simply equating that with our designated rate of change that we wanted that to be. Then we're now going to take our step solving for the t variable. And so it's just now bringing us back to a standard algebra problem right here. We're solving an exponential equation. So my first step here, now let me make some space for my board. So the first step here is to divide both sides of our equation by this coefficient. Okay. So dividing both sides by that, 424. Okay, and there are quite a few different ways how people can approach that. Okay, and then now I'm looking at e to the 0.053 t to equal whichever. Now I hesitate to keep coming back and forth with my calculator, so I leave all this here as a fraction. But viewers who follow my video can also go ahead and get a calculation for that and do the next step. Okay, but I just leave that as a fraction here. But now what we have, it's a value here. So now we have an exponential function e to the some coefficient t, right, equal a value. So to solve for t value from this equation, what we do here is simply take the natural log of both sides. Well, the reason taking the natural log is because I'm having base e here, so it's a good choice of the log. Even though you can go with log base 10, it's more like an algebraic understanding. Okay, so I'm going with natural log. So here the natural log, taking natural log of both sides, e to the 0.053t, right, is to equal natural log of 938.92 all over 424. And so you can see that if anyone attempting to get this calculation, you can see that we have to get the quotient inside first, then we apply the natural log on top of that. All right. And then again, I'm hesitating to keep coming back and forth with my calculator, so I'm deciding to leave all that here. Just be aware that it's an actual value. Okay. And now I'm going to look on my left-hand side right here, taking the natural log. Now, we have learned that logarithm, when we have power, logarithms applied on a power, then we can bring that power, that exponents to the front right here. So that becomes really just 0.053 t times natural log of e. But natural log of e is just simply 1 itself. So now we don't have to write it anymore. So in other words, my complete equation now is 0.053 t is equal to natural log of all that 938.92 all over 424. Okay, and so now solving for t at this point is a quite simple work right here, just simply dividing both sides by that expression. And so that means my final t is going to be whichever comes out from natural log of the 938.92 divided by the 424. Okay, all that there, and we're dividing that by a 0.053. Okay, and so now I'm going to spend some time a little bit doing my calculation. All right, so final calculation of mine shows, allow me to write that in a little amount of space right here. So what I'm looking at here is 14, t equals 14 after this calculation. Okay, so my t value equals 14.0 18.99 years right here, rounded to 2 decimal places. Okay, so this time here, the problem is indicating that time is in years. So it takes that many years. At that particular year, 14.99, nearly 15 years later, right? Nearly 15 years later, after the day we did the investment, then the rate was growing, would grow at $938.92 per year. Right there. Okay, and now we are looking into part D of the example. So just like I have said earlier in the general discussion of rate of change, then you see by default now for anyone learning calculus, then now rate of change means an instantaneous rate of change. So unless being specified otherwise to be an average rate of change, which is in this case, that's what it is, then we're going to work with an average rate of change. So this problem now in our part D is specifically looking for what is the average rate of change, right, of the future value in the account between year 25 and year 27. So between these, now we have a definite interval to look at. We have a finite interval to work with. Okay, and so now this problem is actually easy. It's a simple thing that we have worked with so many times throughout our it's things that we work with in our algebra courses so oftenly. I just need to recall that our future value is 8,000 e to the 0.053t. That's our future value modeling function. And so average rate of change, recall from our general discussion video lecture, and also you can recall from your algebra understanding that all we need is just a final value. And here this is from between year 25 and year 27. Okay, so that's the given interval. So that means the final value has to be at year 27. So I'm going to substitute in f of 27. I'm going to need to subtract. It's the difference of final value and initial value. And so initial value is the future value at year 25. Okay, and then I'm going to divide it by the final time, year 27, minus the initial time, year 25. That famous difference there, that famous quotient, the difference quotient here is this is average, okay, rate of change. That's what it is again. Okay, and so now it's just a matter of simply doing the calculation. And I am going to take another couple of minutes to do the calculation here. All right, so final calculation of mine shows that this average rate of change turned out to be $1,682.78. Okay, and this is, of course, our money, so we're going with 2 decimals. Okay, and that is the average rate of change, how fast our money is growing on average in between those 2 years, year 25 to year 27.